You ever get that feeling, that feeling?
Yeah.
Like the universe is hiding something big, something truly mind-blowing, just out of reach.
Yeah.
That's the feeling I get from this research. It's like, whoa.
Yeah.
Listener, today we're talking Higgs boson, but with a twist.
Okay.
We're not just recapping what the Higgs is.
Right.
This is going deep into exotic decays.
Yeah.
And this stuff could rewrite what we know about, well, everything.
It's pretty amazing. Yeah. What we're looking at here is this research paper.
Yeah.
And it's a mouthful, so get ready. Prospects for exotic H-bow decays and single and D-Higgs boson production at the LHC and future hadron colliders.
Oh, yeah, that's dense.
It's a mouthful, but it's looking at basically whether the Higgs boson breaks down in ways we haven't even considered.
Okay, so before we get too far, I remember the Higgs boson from school, but honestly, it was like one of those important but kind of confusing things.
Yeah.
Could we just, like, Higgs 101, why does it matter so much?
It all comes down to mass, really.
Okay.
Like, why do some particles have a lot of it, others almost none?
Right.
Higgs helps explain that. So imagine a field, okay?
Okay.
It's everywhere, all of space. That's the Higgs field.
Got it.
Some particles moving through it, they're like wading through molasses, that interaction. That's what gives them mass.
So the more they get stuck is how massive they become.
Exactly. And the Higgs boson is the particle associated with that field.
Okay.
Finding it back in 2012, huge deal, confirmed what we thought for decades.
Right.
But now it's about understanding it better. And that's where exotic decays come in.
Right, because just when we thought we knew it, this paper's like, hold my beer.
Pretty much, yeah. The Higgs might have some surprises.
It's like, it's got secrets.
The paper dives into a scenario where the Higgs boson might decay, meaning it breaks down into other particles, and it does it in a way that we haven't actually observed.
Okay.
It's a whole new thing.
So this HEE4 thing, that's the secret code.
You could put it that way.
But seriously, can we break that down? What is that?
Think of it like a chain reaction.
Okay.
Is the Higgs, right?
Right.
This research says it might decay into two exotic particles.
Exotic, meaning?
Meaning we haven't discovered them yet. They're theoretical.
Oh, wow.
And those are unstable, so they decay further into 4 tau particles. That's the 4 part.
Tau particles, are those like mini Higgses?
Not exactly. They're more like heavier cousins of the electron.
Okay.
They exist on their own, but they don't last long.
I see.
That's actually part of why this whole decay is so interesting.
Okay, so we've got Higgs to exotic particles to tau particles.
Right?
But what makes it exotic? Is it just because it's new?
That's part of it for sure. Our current understanding, the standard model of particle physics,
Right, I've heard of that.
it doesn't predict this decay should happen a lot.
So finding it would kind of throw a wrench in
It
things.
would be huge. A major clue that there's something beyond the standard model.
Whoa.
Something new, something fundamental that we don't get yet.
That's amazing. And this decay, it'd stand out, wouldn't it?
Yes, exactly. A clear signal to find amidst all the chaos of particle collisions.
Like a clear footprint in the sand or something?
Yeah, you could say that. More like a specific seashell on a beach. But there's a hurricane going on at the same time.
Intense, but okay, I get it. It's a lot of data.
Massive amounts, and that's where the LHC comes in.
Right, the Large Hadron Collider.
Exactly. World's most powerful particle accelerator.
Smashing protons together near the speed of light.
Creating those collisions, hoping to make Higgs bosons.
So how do they even search for these decays in there? It seems impossible, like finding a needle in, well, you said it, a hurricane on a beach.
It's complex, but the paper's got a strategy. First, selection cuts.
Selection cuts.
Like filtering your email, you get tons of messages.
Way too many.
Right, but you filter for what matters. Researchers do similar.
So narrowing down the data from the LHC.
Exactly. They focus on tau particles, specific properties that would only come from this exotic decay.
Like a fingerprint, only this time it's a tau particle fingerprint.
You got it.
But
Yeah.
they go further,
Right.
right? There's something about machine learning.
Oh, yeah, that's where it gets really cool.
Does it ever not?
Once they've got the narrowed down data, they bring in the algorithms,
Okay.
pattern recognition, super powerful stuff.
What kind of algorithms are we talking about?
They mentioned one called XGBoost, really good at spotting those subtle relationships in data.
Stuff we might miss otherwise?
Exactly. Even with all our brain power, XGBoost can pick out Higgs events hiding in plain sight.
That's incredible. Like having a superpowered detective assistant.
That's a great way to put it, but this is where it gets even more wild.
Wilder than a hurricane on a beach with a needle and a tau particle footprint.
Wilder, even. They talk about di-Higgs production.
Di-Higgs, meaning 2 Higgs bosons. at once.
That's it, producing two Higgs bosons simultaneously.
Okay, that sounds unlikely, to say the least.
It's incredibly rare, but not impossible. That's the key.
Okay, so what can we even learn from two Higgs? Why is that so important?
Think about it. Observing something that's so improbable, that means we're on to something.
Right, because if it did happen, it would tell us something big.
Exactly. One big thing is the Higgs self-coupling.
Okay, now you've lost me. What's self-coupling?
It's how strongly the Higgs boson interacts with itself.
Wait, so it's not just about how the Higgs interacts with other particles to give them mass, but also with other Higgs bosons.
You got it. It's like figuring out the social life of the Higgs boson. We think they can interact with each other.
The plot thickens.
But we don't know how strong that interaction is, or even really what governs it.
And measuring that, that's the self-coupling.
Exactly.
And that's information we can get from these di-Higgs events.
You see, the rate at which these di-Higgs events occur is directly related to the strength of this self-coupling.
So even if we only see a few, it could tell us a lot.
A lot. It'd be huge for our understanding of the Higgs field itself.
So each of these di-Higgs events is like super valuable.
Incredibly valuable, but also incredibly rare. Even the LHC might struggle to find them.
Is that where this Future Circular Collider comes in? The FCCH?
You're way ahead of me, but yeah.
Well, we did talk about it a bit in the last episode. Got to stay sharp.
The FCCH, still in planning, but it'd be a huge leap forward.
Bigger and better than the LHC.
Way bigger, like 100 kilometers around and higher energy collisions.
So if the LHC is like our best telescope now, the FCCH is like the James Webb Telescope of particle physics.
Exactly. That increase in energy means more Higgs bosons, more di-Higgs events, and a better chance of seeing those exotic decays.
Turning up the volume on a faint signal.
That's it. The FCCH would be a game changer for sure.
Okay, so this is all mind-blowing. I got to ask, why should someone like me or our listener who isn't a physicist care about any of this? What's the real-world impact?
It's a good question. It gets to why fundamental research matters. On one hand, this is about understanding the universe. Like, what are we even made of?
Right, the big question.
The fundamental laws, that's what we're searching for.
It's like we're trying to read the universe's source code, figure out how it all works.
And just like understanding code can lead to, new software, better apps. Understanding physics could mean tech advancements we can't even imagine.
So this research, maybe no smartphones coming out of it next year, but
right.
It's setting the stage for something big eventually.
Exactly. Think about it. The electron discovered what? Late 1800s?
Yeah.
Didn't have the internet then?
Definitely not.
Took decades, right. But that discovery led to a century of progress. Who knows what the Higgs could unlock?
So pushing the boundaries, even if we don't know what's over the horizon.
That's the spirit. And what's cool about this paper, even if they don't find this specific decay, the methods they made, the analysis, that's useful for future research, no matter what.
Oh, so they're like creating new tools for the physics toolbox.
Exactly. Whether or not they crack this code, those tools are there for the next mystery.
The journey and the destination, as they say. Speaking of, this has been a journey.
It has.
Higgs, exotic decays, the FCC, even machine learning. It's wild how it all connects.
It's all connected, and, we've barely scratched the surface.
There's always more.
Oh, yeah, dark matter, what about that? Or the Big Bang, what started it all?
The big questions.
Those are the ones keeping physicists up at night, and this research, it's a step towards answers.
Maybe even answers that change, well, everything.
You never know.
If anyone wants to dive deeper themselves, the paper we talked about, it's Prospects for Exotic HR Decays in Single and Di-Higgs Boson Production at the LHC and Future Hadron Colliders.
Quite a title.
By Amit Adhikari and his team. Find it online if you're up for it.
It's a wild ride, but one last thought. We've been talking Higgs, right? Shaping the universe.
Yeah.
But what about the stuff we don't see? Dark matter, dark energy. Could the Higgs be involved there too?
Whoa, now that's a question to ponder.
It's a big one. And it'll be years, maybe decades before we know.
The mystery continues. That's what I love about this stuff. Well, listener, that's our deep dive for today.
Until next time.
This has been The Deep Dive, signing off.